Hello students, welcome to JCE Connect series of lectures. So in previous lecture we have seen the construction of velocity triangle and how the velocity triangles are been constructing at inlet as well as at outlet, and we have discussed about various components of uh, velocity triangle, and we have discussed this velocity triangle will be very much useful in turbo machineries, where the velocity triangle or the velocity diagram is a triangle representing the various components of a working fluid in a turbo machines. And the velocity triangle may be drawn both at inlet and outlet sections of any turbo machines, and from the velocity triangle we can analyze the velocity of the fluid, and the vector nature of the velocity is being utilized in this particular triangle. And most basic form of velocity triangle consists of the absolute velocity v, then relative velocity vr, and the blade velocity u. And about the construction of a velocity triangle we have discussed in previous lecture. Please go through that lecture and try to understand the construction. And after construction of velocity triangle, how the force experienced by the jet and work done by the jet can be calculated. Force experienced by the jet and work done by the jet. So this is very important derivation. And considering the velocity triangle, you have to construct a velocity triangle at inlet and outlet of the blade, and from the velocity triangle you have to calculate the force experienced by a jet as well as work done by the jet. And at inlet velocity triangle, you know the various components uh, as explained earlier, where v1 at inlet velocity triangle, v1 represents absolute velocity of jet at inlet, and angle alpha is angle made by v1, that is called guide blade angle, or angle at which the jet enters the vane. Then theta represents the inlet blade angle, that is a blade angle at inlet, and vr1 represents a relative velocity at inlet, and vw1 is a whirl velocity at inlet, and vf1 the flow velocity at inlet. These vw1 and vf1 are the components of v1, the components of v1 in horizontal as well as in vertical direction. And the jet will enter with a velocity vr1 into the blade passage, and it will be making an angle of theta with the horizontal. And when you resolve this vr1, one in a vertical direction and one in a horizontal direction, you will be getting vr1 cos theta and vr1 sin theta. Okay, so vr1 cos theta is, this is the horizontal component of vr1, we get vr1 cos theta as well as vr1 sin theta we get. Similarly at outlet velocity triangle, look at the outlet velocity triangle. Again there are various components there. The pi represents the outlet blade angle, that is blade angle at outlet. Then vr2 represents the relative velocity at outlet, vf2 represents the flow velocity at outlet, vw represents the whirl velocity at outlet, and v2 is the blade velocity. And it is very easy to construct the velocities triangle at inlet as well as at outlet. Once we construct the velocity triangle at inlet and outlet, then with respect to these two triangles we have to calculate the force experienced by the jet on the vane, that is force experienced by jet on the vane. We have to apply the impulse momentum principle here also. So applying impulse momentum principle, applying impulse momentum principle or impulse momentum equation, then force in x direction So Fx will be a rate of change of momentum in x direction. Then Fx can be written mass per second into bracket initial velocity minus final velocity. So here mass of fluid striking the vane per second. Here mass of velocity or mass of fluid striking the vane per second. So he equal to mass per second, which is equal to as we know density equal to mass by volume, so we can write density into area of jet into velocity. We get density into area of jet into velocity. We can get rho is density is a rho into area into velocity. Here velocity to be taken relative velocity. With this velocity the jet is entering into the blade passage. If you look at here, so it will be entering with relative velocity, not absolute velocity, because vane is also moving, so it will enter with a relative velocity. Hence we have to take the relative velocity, that is VR1 at inlet. So this is a mass per second. We have to substitute here. Then Fx will be rho a VR1 into bracket initial velocity. So here we have to take the initial velocity with which the jet, initial velocity of the vane. So since it is entering with VR1, so like this, so I'll draw here. So jet will be entering with this velocity. This is VR1, which is making an angle of theta here. Okay, then we want force in x direction. You have to resolve this VR1, one vertical and one horizontal. When you resolve this you get VR1 sine theta, and this is VR1 cos theta. Okay, then initial velocity in x direction, we have to take VR1 cos theta. So here I'll write VR1 cos theta initial velocity minus final velocity. Final velocity again same, at outlet velocity triangle you have to look. So this is the initial velocity, then outlet velocity you have to take VR2 cos pi. This is the VR2 exiting. Again you have to resolve at outlet. Similarly here at outlet, when it is exiting like this, VR2 and this is making an angle of pi here. When we resolve this one, this is one component, this is other component, you get here VR2 cos pi. Okay, I hope you understood this one. Then you write final velocity as minus, again this is opposite to the direction of incoming jet. So this one opposite to the direction of incoming jet. This is going opposite. The incoming jet is in this direction. The incoming jet is in this direction, and the jet leaving in opposite direction. So you have to write minus of minus VR2 cos pi. Then, but from velocity triangle, that is figure, velocity triangle figure. If you look at a velocity triangle figure, what is VR1 cos theta? See, what is VR1 cos theta? If you look at this velocity triangle, this is a VR1 cos theta from here to here. So VR1 cos theta is what? VW1 minus U1. VW1 minus U1. So from VR1 cos theta will be VW1 minus U1 from inlet velocity triangle, and VR2 cos pi is what? VR2 cos pi is what? You just look at the outlet velocity triangle here. So one way I taken this one. So VR2 cos pi it is. This is actually VR2 cos pi. This is VR2 cos pi. This component. Then this one. When we resolve this one, we are resolved here. Just look at this figure. So if I shift here, you will get like this triangle. Then this is VR2 cos pi. Okay, VR2 cos pi. That same I written here, VR2 cos pi. That is nothing but U2 plus VW2. U2 plus VW2 from outlet velocity triangle. U2 plus VW2. Okay, then substitute in the above equation, we get Fx equal to rho a VR1 into bracket VW1 minus U1, then plus U2 plus VW2. And since here, since U1 equal to U2, so if you take the velocity of the blade at inlet as well as at outlet, that is the velocity of the blade, if you take, so this is the disc or the impeller, it is the shaft, it consists of blade like this. So if you take this blade, one blade, this is the inlet and this is the outlet, when the jet strikes this one, this will be moving forward. Along with this also moves forward. So both the velocities are same here. This end and as well as this end, the velocities are same. So considering the velocity of vane is same, so U1 equal to U2 equal to U, velocity in the direction of jet of motion, and when U1 equal to U2 is equal to U, also VR1 is equal to VR2. So here VR1 is equal to VR2 means we have assumed the blade passage, this blade plus is very smooth. Whatever velocity with which the jet is entering, the same velocity it is leaving. So VR1 is equal to VR2. Then after this we have assumed U1 equal to U2 equal to U and VR1 is equal to VR2. Then what the equation we get finally? When you substitute in the above equation, we get Fx equal to rho a VR1 into bracket VW1 plus VW2. So here both will get cancelled here. When you are assuming U1 equal to U2, then these two get cancels. You will get rho a VR1, VW1, VW2. Then this is the equation what we get. Okay, so after this one, then next what we get, this is the force in x direction. VW1 is the whirl velocity and VW2 is the whirl velocity at VW1 is whirl velocity at inlet and whirl velocity at outlet. Then some conditions here, conditions to be considered, that is condition 1, when beta equal to 90 degree, when beta becomes 90 degree. When beta becomes 90 degree in this figure, just look at this figure. So if you take the angle beta here, this angle beta is acute angle. When it becomes 90 degree, this beta, just I'll draw here, just look here, when that angle becomes 90 degree, this one like this is like this, like this. Okay, so this is the U, that is U2 at taken at outlet. When this becomes 90 degree beta, When beta and beta becomes 90 degree, and this will be taken in this figure. When beta becomes 90 degree here, see, when beta becomes 90 degree, so this V2 is equal to VF2. V2 will be equal to VF2. V2 is equal to VF2. And when beta becomes 90 degree, what about whirl velocity? Whirl velocity get vanished here. Will not get whirl velocity here. So it get merged. So earlier it was like this. Now when it becomes a 90 degree, so whirl velocity will be 0. So VW2 will be 0 here. When beta is 90 degree, V2 becomes VF2, and this is pi, and VW2 is 0. Then the above equation becomes Fx will be rho A VR1, that is VW1 only, when beta is 90 degree. Second case, when beta is greater than 90 degree. So this case is, this one is when beta is less than 90. This case is when beta is 90, when beta is 90 or more than 90 degree. So if this beta angle, beta is what? Here beta is, what beta represents angle made by the velocity V2 with the direction of motion of wave. Angle made by the velocity V2 with the direction of motion of wave. Okay, so this beta is angle made by the V2 with direction of motion of wave. When this beta is greater than 90 degree, so how will be the figure? Will be like this figure, and this will be as it is, that is VR2 will be as it is, and V2 will be like this. This V2 becomes like this. This is to be V2, and this vertical component will be as it is, that is VF2, and this whole will be U2. From here to here is a U2, and this will be what? VW2, and this will be component of VR2 cos pi. So now here you have to consider this one, this angle made by V2 with horizontal. I am taking angle made by V2 with horizontal, which is greater than 90 degree. So previous angle made by V2 with horizontal was 90 degree, and first case was angle made by V2 with horizontal was acute angle less than 90 degree. So for less than 90 degree, this was the equation we have got, and for 90 degree the whirl velocity get vanished, and if beta is more than 90 degree. So these cases are very important while solving a problem. If beta is more than 90 degree, this is angle at which the jet is exiting from the vane. So in problem they'll give the jet is exiting from the vane by making an angle of 90 degree, or by making an angle of less than 90 degree or more than 90 degree. If V2 making an angle with horizontal is greater than 90 degree, so what we get here, Fx will be, then Fx will be what? If you want to calculate Fx, what we get Fx here, rho AVR1, then you will get VW1 minus VW2, we get VW1 minus VW2 we get. Okay, so we get minus VW2 here when beta is more than 90 degree. This is the equation we get finally. So in general we can write Fx equal to rho AVR1 VW1 plus or minus VW2. This is the general equation. So depending on the value of beta, that is angle made by V2 at outlet, you can write plus or minus, or some term get vanished, that depends. Okay, so this is the final equation, that is force in x direction. Then work done by the jet. Work done by the jet is work done per second, work done by the jet. Then we write Fx into velocity of plate. Then Fx we know, that is rho a Vr1 into Vw1 plus or minus Vw2 into u. So this is work done per second. Then efficiency of the jet, if you want to calculate efficiency of the jet, then work done per second output by input, kinetic energy per second. And here kinetic energy per second, again as usual you have to take kinetic energy per second will be half mv square. This is the formula, but this is per second, we get rho a v cube, the same formula to be applied here. So with this you have to calculate kinetic energy per second, then work done per second is this one, then finally you get the efficiency. I hope you understood this derivation. So very important, the derivation here. So only thing is the conditions what we apply here. When beta is more than 90 degree, you will get a VW1 minus VW2 here. So when beta is less than 90 degree, so this was the equation, we got the VR2 cos pi. So this VR2 cos pi, here look at this figure. So how we have got the minus sign here. If you take VR2 cos pi, what we write VR2 cos pi here? VR2 cos pi will be what? U2 minus VW2. So when you substitute in this equation here, so Fx will be what? We get rho a Vr1 in this, like this, rho a Vr1 Vw1 minus u1, because u1 equal to u2 we're having. So u1 u2 get cancels, we get Vw is Vw1 minus u1, Vw1 minus u1, then plus u2 minus Vw2 we get, but u1 equal to u2, this just cancels, then finally you get rho a Vr1 Vw1 minus Vw2 we get when beta is more than 90 degree. So I hope understood these conditions. So very important conditions. Okay, and derivation is also very important. Force experienced by a jet, many a times the question asked in an exam, and also work done by the jet. Okay, so taking velocity triangle into account, you have to get the force exerted by the jet in x direction, and when beta is less than 90 degree, and when beta is 90 degree, this is the force, and when beta is more than 90 degree, then finally this is the efficiency of the jet. Then work done per second we have to calculate. Again, in general the equation can be written like this. Okay, thank you.